Okay, next up we have Mike McCulloch is going to come talk to us about some of the research he's doing, kind of exploring thunder radiation and how it might be of relevance to the stuff that we're thinking about and talking about. So let's, Mike, if you could introduce yourself. I'll bring up the truck.
Okay, so hello. So today I'm going to talk about quantized inertia, propellant-less thrust, and interstellar travel, obviously. And I see the problem being how to get from the Sol star system to, say, Casimir Centauri B. So I'll try and come back to that at the end. I'm from the University of Plymouth. And a brief breakdown of the talk. I'm going to talk about the problem that inspired me first, the galaxy rotation problem. Talk about my suggested solution, which is quantized inertia, apply it to propellant-less thrust, and ask whether it can get us to Proxima Centauri in 10 years. Okay, so the big problem is the galaxies spin faster than physics predicts they should. So here's the Andromeda galaxy, billions of stars in it all spinning around. And if you consider one star, it's attracted toward the centre by gravity, of course. You can work this out by counting the stars that they see. Also, there's something called inertial mass, which tends to keep things moving in a straight line. So the star wants to go off into outer space. There's a centrifugal force outwards. And we can measure the rotation rate of the stars, and we find that the centrifugal force on them is much bigger than the gravity that they should be feeling. So this is a problem. This was first found by FISW2 back in 1933, and by Theory Rooting a bit later in 1980 or so. So most astronomers react to this by adding dark matter to the galaxy. They calculate the amount of spin that general relativity should predict. Where they find it doesn't match, they add dark matter, extra matter to the galaxy arbitrarily to make it all work. So I don't like this solution very much, as you can probably tell. So I've been thinking about inertial mass. So inertia has always been a bit of a mystery. Things tend to keep going in straight lines, like this ladder on top of a lorry. Lorry stops, the ladder keeps going, because it has inertial mass. And inertia has never been understood, in my opinion, just assumed. It's almost like language, things keep going in a straight line. It's not due to the Higgs field, which only explains the mass of the quarks. We need 1,000 times that force to explain inertial mass. So I'm going to propose that inertial mass arises from a kind of mix of relativity and quantum mechanics. So I'll start with the quantum mechanics, and this was mentioned by Jeremy as well, of course. I'm doing it in a slightly more graphical way. Werner Heisenberg, he wrote down his famous uncertainty principle, which says that the uncertainty in momentum of an object, quantum object, times its uncertainty in position has got to be more than a particular number. This means that if you shrink the space that you're considering, so dx, you look at smaller and smaller regions of space, the momentum within that space becomes more and more uncertain. And so on a smaller scale, space is like a sea of virtual particles, as Jeremy was saying. These particles can be thought of as particles, so you might have a particle pair, one is emitted to conserve momentum, and another one is emitted in the opposite direction, and you recombine a short time later. But in quantum mechanics, of course, it's a bit schizophrenic in that you have particles and waves associated with them, so there are waves too, and I've shown that with the red curve. The proof of this is the Casimir effect. So Henry Casimir said that, okay, if this quantum vacuum exists, then why don't you put two conducting plates in very close together in the vacuum? What will happen then is that waves, particle waves that fit between the plates, like this one has a node at either end, can exist, but other waves, for example this one with an antinode there, will be damped or will disappear, will not be allowed. So they will disappear. So now you've got more quantum particles banging into the plates from outside than there are on the inside, pushing them out. So the plates should move together. And in fact, this has now been observed in many cases by Lamoureux in 1996, for example. So this quantum vacuum really does exist. So my background is in ocean physics. So there's been a lot of oceanography mentioned today. So I'm going to start with an ocean analogy to explain what I'm saying. So we have a ship and a dock. Lots of waves out to sea, as you would expect. But between the ship and the dock, there are fewer waves. And this is obviously because of the sheltering, but there's also another factor at play. Waves like this, that have a node at the ship and the dock, will not be damped. This is no friction. It's not moving up and down at these positions. Any other kind of wave, most of the kind of waves will be damped and will disappear. So you'll expect there to be fewer waves between the ship and the dock, so the waves will push the ship to the dock. So this is like the maritime Casimir effect, which I know was mentioned. So I now have to introduce a very strange kind of idea, but another kind of dock or wall or plate is called a horizon in physics. So imagine that you're so shocked by what I'm saying, you run away very fast, and you get in a jet plane and zoom away, faster than the speed of sound. Then you could say that I'm behind an acoustic horizon for you. You cannot get information from me acoustically because the way sound waves coming from me will never get to you. So this is the idea of a horizon. It's an information boundary, and it depends on who you are. So somebody who became quite famous looking at horizons is Stephen Hawking. So he looked at the black hole event horizon. So if you have a lot of mass in the centre here, it pulls light in, light cannot escape. So for somebody out here looking in, they will never see what's inside there. It's a black hole. Stephen Hawking said what would happen if we emit one of these quantum pairs on the horizon. One would go out, one would go in. The one that goes into the black hole will disappear, of course, and then the other one will not be able to recombine with its twin, so it will be released. And this is the origin of Hawking radiation. So this is where that comes from, which has not been seen yet. About the same time, just afterwards, Bill Unruh in Canada, that's him, said that if you have an accelerating spaceship accelerating in this direction, then similarly, information from this area will never get to it because it's accelerating away from that area. So there will be what's now called a Rindler horizon behind the spaceship. In the same way, if you get a particle pair emitted, one will come out, one will go in. The one that goes behind the horizon will disappear from the point of view of the ship and will become what's now called Unruh radiation after Bill Unruh. So has Unruh radiation been seen? Well, it's very difficult to see. Its wavelength is 8 times the speed of light squared of the acceleration. So for terrestrial accelerations, it's about 7 light years long. So it's hard to see. But you can see it if you use very high accelerations. And there was an experiment by Bevis Lewis where they got a gold nanotip like this. They shone a laser on it. Plasmons went around the bend very fast, and they saw light come off, which looked just like Unruh radiation. So this may have been seen. So the model I'm going to suggest for inertial mass is the following. We have an object here which is accelerating to the right. Relativity produces a horizon behind it here. There are lots of quantum waves, Unruh waves all around it. Unruh waves are isotropic, they're going in all different directions. But between the object and the horizon, I'm going to only allow certain waves, as in between a ship and a dock. This is because if you have a partial wave it's a bit philosophical, the reason I'm doing it. If you have a particle going through the horizon,